Hi, I'm Zenith. I will make this video on mode Penrose pseudo inverse. We'll talk about where this comes from. We'll do an example, see a little bit of code, and see what its applications essentially are, right? All right. So first thing, generally, if a matrix is square, so what we do is we just take its inverse and we solve the equation as follows, right? So if we have ax equals y, we take a inverse on both sides, and a inverse a becomes identity matrix, and the vector we're solving for becomes a inverse into y, right? That is when we can take an inverse. But what about like situations where we can't take an inverse? For example, when you have non-square matrices and stuff like that, right? So what do these situations of a non-square matrix look like, right? So either you have too few equations for too many variables, or the other way around. You have too many equations but not enough variables, right? So an overdetermined situation is when you have few variables but more number of equations. And so as you can see in the example where you have multiple lines intersecting and you want one solution, but all of these three lines do not have a common point of intersection, right? So we'll talk about what the pseudo inverse, the solution that it gives you essentially means in a graphical term, right? And in an underdetermined system, you have too many variables but not enough equations, right? So to solve stuff like this, to solve equations like this, you can't just directly take an inverse because it doesn't exist, right? So you have to take a pseudo inverse. Right, so let's talk a little bit about where this comes from, right? So the proof for it. Let's talk about an overdetermined problem first, right? So in an overdetermined problem, pardon my handwriting, right? You have a matrix and essentially let's say your matrix is A V equals Y, right? And you have to find the V vector or the solution to it. So your loss function in this case looks something like this, right? So what do we do to minimize this loss function, right? So we just take the gradient for this, right? Or we just differentiate it with respect to V and we equate that with zero, just like how we do with polynomial equations, right? So we just do this equals zero. And this is gonna be nothing but, uh, this is gonna, when you compute this, which I suggest you should try, this is gonna come out as this. And when we solve this is gonna look something like what we need to find here now is the vector v, right? And how do you find the vector v? You take the inverse of A transpose A. Now understand that A transpose A is going to be a square matrix, right? Just the inverse हम ले सकते हैं for the inverse for which we can find. So that's going to look something like A transpose A inverse into A transpose and the y vector. This entire entity is now going to be your pseudo inverse, right? What about an underdetermined system? Right? In an underdetermined system, the solution that you get is essentially the one with the smallest norm, right? In an overdetermined system, as we saw previously, when you have a graph that looks something like this, and you have multiple lines, right? Something like this. So the solution that it gives you is essentially the one which has the minimum least squared error, right? So for this, the solution might lie somewhere here for which the error is the least, right? In an underdetermined system, let's say it looks something like this, the solution that it will give you is going to be the one with the least norm. So when you draw a circle like this, the solution that you get with the pseudo inverse is this one right here, where it's tangential to the circle, right? So here your loss function looks something along the lines of this. Right? And when you differentiate it with respect to x, you get this. Which is supposed to be 0. Right, so we can rewrite this like so, and then you get x equals minus A transpose mu, right? And then you differentiate it with respect to mu, and you get something like this, minus B equals 0. And then you just substitute, right? You substitute the value of x here, and you get minus A transpose mu minus B equals 0. And you get mu as minus A transpose inverse B, right? And then you just put this back into this equation, and you will get your, from here, you get your x as A transpose into A transpose inverse B, right? And this thing becomes your pseudo inverse, right? So for overdetermined system, your pseudo inverse looks something like this, and for your underdetermined system, it looks something like right. So this is the proof that we just discussed. You can look up more about it on your own. I'll also link the paper in description from which I took it. The example one essentially shows you what an underdetermined system looks like, what the pseudo inverse for it looks like, and example two shows you what it looks like for an overdetermined system, right? Then coming on to some of the properties, these four conditions are essentially the conditions that you need to check whether a matrix G is a pseudo inverse for A or not. Right? What I mean by that is if you're given a matrix G and you want to find out whether or not it is the pseudo inverse for A, then these four conditions are going to be sufficient. If G and A satisfy these four conditions, then necessarily G is the pseudo inverse of A, right? Another fun property here is that note the pseudo inverse of A into A is not equal to A into pseudo inverse of A, right? Unless A is square, right? But also both of these have to be Hermitian. And A pseudo inverse into A is going to be I, but as we saw above, A into A pseudo inverse might not be I, might not be the identity matrix. All right. So here, this is, so when you have pseudo inverse of A into A, this, that translates into the identity matrix and you get A here. Similarly, here, pseudo inverse A into A translates into identity matrix and you get G here, right? The transpose for this for AG is going to be AG only. And similarly for GA, it's going to be GA, right? Another interesting fact about pseudo inverses is that for any matrix, it will always exist, right? If you take up any matrix, a pseudo inverse for that always exists and it's unique in nature. So you can't have more than one pseudo inverses for a given matrix. All right, consider this system of equations ax equals to y, right? Here, let's just assume that this is an overdetermined system where you have more equations than you have the number of variables, right? So the solution, this is an overdetermined system. So the solution for it would look something like this, as we just discussed. And note that the pseudo inverse of A into Y will give you an approximate solution for X, right? The solution with the least error. That's what you get. There is no exact solution to the problem. So let's just take up this example, right? What's happening here is that you have two variables, but you have three equations, right? So you have to first find the pseudo inverse of A. A is going to be the matrix of the coefficients, right? And as the formula we just derived, you use that, you solve that, try to do it on your own, and you come up with the pseudo inverse, right? And then your solution is going to look something like this. So you take pseudo inverse of A, or you multiply both the sides with the pseudo inverse of A, and A pseudo inverse into A becomes identity, and you're left with the solution, the closest approximation of X, your X vector, right? Now, this isn't exactly the solution that we need, right? So it's very close to it. Why does this happen? I've already told you that there is no exact solution to overdetermined problems, right? What you're essentially getting is a very close approximation for it. So the equations we saw, when you map them onto a graph, they look something like this, right? Note that there is no one point where all of these lines are meeting, right? There are three different points where these lines intersect, but there's no one point or one solution for all of these three equations. So what do we get exactly from the pseudo inverse that we've just found, right? What we get is a solution with the least error, right? This is what where approximately our solution lies, right? And when you find out the error for this, it's going to be the least error solution. Cool. This is also what we talked about. A pseudo inverse A is I, but the vice versa is not true. These are some other useful properties for pseudo inverses. These are also some of the general properties. Note that rank of pseudo inverse is going to be the same as that of A transpose or A pseudo inverse A, and so on. And same goes for the null space. You can try to prove this on your own using the basic properties, the four postulates that we saw at the very beginning, right? That should be fun. Right. An alternate way, this was how you do it by hand, right? An alternate way of finding out the pseudo inverse is through SVD, right? That's how it also happens in like NumPy or whatever code you're writing. That's how your computer solves it. It finds out it breaks it down, it does the decomposition, and then it finds out the pseudo inverse, right? Let's check out how it exactly works. Right. So let's just consider matrix A that looks something like this. And what we're going to do is we're going to take the SVD for this. We get U, D, and by default, the SVD method gives us V transpose, right? So this is what U, D, and V transpose look like right now. Cool. What we need to do next is we need to diagonalize D and we need to fix its dimensions, right? So D must have the same dimensions as your other matrices, right? Then just verifying if that's right, you take the dot product and you get the same matrix A back, right? So the method SVD is correct. What we do now to find pseudo inverses, we find D plus. What does D plus look like? D plus is going to be the inverse of D, right? How do we find that? First of all, we diagonalize D. Then we take the inverse of D using the function itself, right? Post that, we fix its dimensions as before, and we take the dot product again, right? So as we saw previously, the pseudo inverse or the A dagger, it looks something like it's the dot product for V, D plus, and U transpose, right? Since we already get V transpose from the SVD method, we take its transpose again. Then we dot it with D plus dot U transpose, right? So this is what your pseudo inverse looks like. And NumPy already has a built-in method for finding pseudo inverses as well. So you can verify whether what you've gotten is right or not. Cool. So if we multiply A with A dagger, you get something like this. And when you multiply A dagger A, you get a matrix that is really, really close to the identity matrix, right? So essentially, you're getting the identity matrix itself. You can play around with the code a little bit and try to verify the rank and nullity theorem through this as well. I would really encourage you to try that. Also, like, we can use this more Penrose